else? Population dynamics. The study of population dynamics focuses on the complex interactions between biotic and abiotic factors that cause variation in population size. So, numbers vary from year to year, place to place, depending on weather, how much food is available, predation, competition. Stability and fluctuation. So long-term population studies have challenged the hypothesis that populations of large mammals such as moose are relatively stable over time. So over here you look at the moose population size, 500 to 2,500 from 1960 to the mid-2000s. And you can see how the population has risen and fallen. Fallen probably due to predation, dramatic collapse caused by severe winter weather, food shortage leading to starvation of more than 75% of the population in the late 19th. Extreme populations fluctuations and have been shown in more commonly in invertebrates such as the Dungeness crabs than in large mammals. So here you can see spikes and peaks throughout the years, more closely tied to the environment. So metapopulations and immigration when groups of populations are linked. So metapopulations are groups of populations linked by immigration coming in and immigration, the red line, leaving. High levels of immigration combined with higher survival rates can result in higher stability in populations. So here, increase, they leave, and then they're increasing again. This is more stable, more common line, more baseline, and this is in British Columbia. Population cycles in the snowshoe hare and lynx. So population counts are based on the number of pelts sold by trappers to the Hudson Bay Company. So undergo boom and boost cycles. So boom and boost cycles are influenced by complex interactions between abiotic factors. I love this one, the global human population. The human population increased relatively slowly until about 1650 and then began to grow exponentially. So here, very slow, wars, diseases, hard life, plague, dipped down, a lot of people died, and now 2000 has increased. No wars, better health, more immunization, better food is available. So here, dip in 1960s due to famine in China. 60 million died. Hard to believe now since China is now one of a major economic power. But though the global population is still growing, the rate of growth began to slow about 40 years ago. Dotted line projected data. Okay. And used to have a very high growth, but with the regime in China, birth rate is limited. So regional patterns of population change. To maintain population stability, a regional human population can exist in one or two configurations. Zero population growth equals high birth rate minus high death rate. They zero each other out. Zero population growth, low birth rate, low death rate. Again, they cancel each other out. So the demographic transition is the move toward the second state. So here, demographic transition in Sweden and Mexico, 1750 through 2050. Okay, so you can see Sweden birth and death rate. Here, much lower. They cross here where death rate around 2000 exceeded birth rate. Mexico, death rate here is much lower than the birth rate, but hopefully in the mid-2000s they will meet. Age structure diagrams. Age structure diagrams can predict a population's growth trend, commonly represented as pyramids, and they can illuminate social conditions and help us plan for the future. So age structure is relative number of individuals at each age, so starting down here at birth to 85 plus. So Italy has a small base, Afghanistan a very large base, the U.S. is relatively even. So age-structured pyramids as of, in your book it talks about 2007, this might be 2005 here, the annual rate of population growth was approximately 2.6% in Afghanistan, 0.0% in the U.S., and 0% in Italy. Okay? You can see how the difference. Infant mortality and life expectancy at birth vary greatly among developed and developing countries. So here infant mortality very low in developed countries, life expectancy pretty high, versus developing countries, higher infant mortality, less industrialized countries, not as much life expectancy, just over 6. How many humans can the biosphere support? For 2050, the United States projects a global population of approximately 7.5 to 10.3 billion people. Without some catastrophe, an estimated 1.2 to 4 billion people will be added in the next 4 decades or 40 years. How many humans can the biosphere support? It is populated. So the estimates of carrying capacity for Earth or the biosphere is uncertain. How much habitable land is there, and also food availability. The ecological footprint concept summarizes the aggregate land and water area needed to sustain the people of a nation. It is one measure of how close we are to the carrying capacity of Earth. The carrying capacity of Earth. So countries vary greatly in footprint size and available ecological capacity. 2 hectares, 1 hectare, hectares is the unit of measurement in almost every other country but the U.S. We do acres. So 1 hectare equals about 2.5 acres. So per person worldwide. Okay, this is available ecological capacity. With 1.7 hectares per person with parks and conservation. So that is decreased if we have green spaces in our biosphere. The U.S. has an ecological footprint of 8.4 hectares per person, but has only 6.2 hectares per person of available ecological capacity because of the wasting of our natural resources. In contrast, New Zealand has 9.8 hectares per person, but an available capacity of 14.3 hectares per person, so it is its carrying capacity. At more than 6 billion people, the world is already in ecological deficit. This is a pretty old graph, 1997. The red dots, ecological deficits. The blue dots still have resources. Okay, so look, we're up here along with Norway, the UK, Japan, Netherlands, Spain. This is the world here. India and China right here. Okay, Sweden, Canada, Australia, New Zealand, they do not have deficits. They have surpluses. Of course, Canada, Australia, New Zealand, huge land masses. Sweden, also a lot of undeveloped